Water breaks the rules of physics. Not one rule, at least 7. And every single violation is the reason you are alive. If water behaved like a normal molecule, if it followed the same laws as every other substance of similar molecular weight, this planet would be a frozen rock. The oceans would be solid ice from top to bottom. Trees could not exist. Your blood could not carry oxygen, and none of it would matter because you would never have been born. All of this, every bit of it, traces back to one bond, one electromagnetic interaction between two elements. And the story of what that bond does, the sheer improbability of it, is one of the strangest stories in all of science. Now, to understand what makes water so dangerous, and I use that word deliberately, you need to understand one thing first, because everything, every anomaly, every violation, every impossible thing water does comes from this single interaction. Let me tell you what it is. Oxygen is greedy. That is the simplest, honest way to put it. On the Pauling electronegativity scale, a measure of how strongly an atom attracts shared electrons toward itself, oxygen scores 3.44, one of the highest values of any element in the periodic table. Only fluorine is higher. When oxygen bonds covalently with hydrogen in a water molecule, it pulls the shared electron pair toward itself. It hogs the electrons, not completely. This is not an ionic bond. The electrons are still shared, but unevenly, dramatically unevenly. That uneven sharing leaves the hydrogen atoms slightly positive, electron poor, and it leaves the oxygen slightly negative, electron rich. The molecule becomes what physicists call a permanent electric dipole, 1.85 DeI, if you want the exact measurement. Positive on the hydrogen side, negative on the oxygen side, with a precise charge separation built into the geometry of the molecule itself. That sounds like a technical detail, a number in a textbook. But this dipole does something remarkable. Because each water molecule has 2 hydrogen atoms and 2 lone electron pairs on its oxygen, it can form up to 4 hydrogen bonds with neighboring water molecules simultaneously, 2 through its hydrogens, each one reaching out to the negative oxygen of a neighbor, and 2 through its lone pairs, each one accepting a hydrogen from a neighbor. 4 connections, a tetrahedral web of electromagnetic attraction. These are not weak attractions. The typical van der Waals force between small molecules, the fleeting, gentle pull that holds something like methane or propane together as a liquid, is roughly 1/10 the strength of a single hydrogen bond. Water molecules grab onto each other with 10 times the force you would expect from a molecule this light. Methane, which has nearly the same molecular weight as water, is a gas at room temperature. It boils at minus 161 degrees C. Water, with its hydrogen bonds, stays liquid up to 100 degrees. Same weight, radically different behavior. The only difference is the bond. To put this in perspective, consider methane. Methane has a molecular weight of 16. Water has a molecular weight of 18, nearly identical. If you knew nothing about hydrogen bonds and someone asked you to predict the boiling point of water based on its molecular weight, you would guess something close to methane's. Minus 161 degrees Celsius. A gas at room temperature gone invisible, evaporated into space. And you would be perfectly reasonable to guess that, because that is what the molecular weight predicts. Instead, water boils at 100 degrees Celsius, 261 degrees higher than the molecular weight would suggest. That gap, that enormous, inexplicable gap, is the hydrogen bond. It is the reason water is a liquid at the temperatures where life exists, rather than a gas that evaporated into space billions of years ago. Most liquids are held together by whispers, gentle, fleeting attractions between molecules that barely notice each other. Water is held together by a scaffold, a temporary but constantly rebuilt lattice of electromagnetic connections, forming and breaking and reforming billions of times per second. Each individual bond lasts only a few picoseconds, trillionth of a second, before it snaps and another takes its place. But at any given instant, the network is there, structured, cohesive, pulling every molecule toward its neighbors with a force that for a substance this small and this light is extraordinary. One bond type, one interaction between oxygen and hydrogen. Remember two numbers, 1.85 Dubai and 104.5 degrees, the angle between the two hydrogen atoms in a water molecule. Those numbers are going to come back, and when they do, they will mean something very different than they do right now. Now here is where water starts breaking rules. And the first rule it breaks is one that everything else in the universe obeys. Every known substance follows the same pattern when it freezes. The molecules slow down, lose kinetic energy, and pack tighter together. The solid becomes denser than the liquid. Iron does this, copper does this, alcohol does this, nitrogen, carbon dioxide, mercury, benzene, sulfuric acid, every substance ever measured, thousands of them, all behave the same way. When you cool a liquid and it solidifies, the solid contracts. It becomes heavier per unit volume. If you drop it into its own liquid, it sinks. Every substance does this except water. When water freezes, the hydrogen bonds do something peculiar. As the temperature drops towards 0 degrees C, the molecules slow down enough for the hydrogen bonds to lock into a stable, permanent arrangement. And the geometry they choose is a hexagonal crystal lattice, a rigid, open structure. Six-sided rings of water molecules, each one hydrogen bonded to its neighbors at precise fixed angles, forming vast channels of empty space within the crystal. The architecture is beautiful, and it takes up more room than liquid water. The solid is less dense than the liquid. Ice floats. You probably learned this in school. You know ice floats. You see it in your glass every day. And it is tempting to treat this as a curiosity, a fun fact, a trivia question, a peculiarity of one particular molecule. It is not a curiosity. It is the single most consequential anomaly in molecular physics. And to understand why, you need to imagine a world where ice behaves like every other solid, where it sinks. Think about a lake in winter. The surface cools first. Ice forms on top. In our world, the real world, that floating ice acts as an insulating blanket. It sits on the surface, slows the escape of heat from the water beneath, and the deeper water stays liquid. Fish survive beneath the ice. Microorganisms persist. The lake's ecosystem sleeps through winter but does not die. Spring comes, sunlight warms the surface, the ice melts, and life continues. Now imagine ice sinks, the surface freezes. The ice, being denser than the liquid below, drops to the bottom of the lake. Fresh liquid water is now exposed at the surface. It cools, it freezes, and that ice sinks too. And again, layer after layer, the ice accumulates on the bottom, insulated from summer warmth by the water above it. Pressed under its own growing weight, it never fully melts. Each winter adds more. Within a handful of seasons, the lake is frozen solid, not from the top down, but from the bottom up, permanently. Now scale that up. Rivers freeze solid, estuaries freeze, shallow coastal seas freeze solid, and with each successive ice age, and Earth has had many, spread across billions of years, the process accelerates. The ice at the bottom of the deep ocean, hundreds of meters down, insulated by water above and under crushing pressure, never encounters enough warmth to melt. Each glacial period adds another layer. The planet whitens, albedo increases. More white surface means more sunlight reflected, which means more cooling, which means more ice. A runaway feedback loop with no exit. The planet becomes a snowball, not metaphorically, not regionally, a dead, white, frozen sphere from pole to pole. And here is the cruelest part. It would be self-reinforcing. Ice is white. White surfaces reflect sunlight. More ice means more reflected sunlight, means less absorbed. Heat means more ice, a runaway loop with no natural exit. The planet would freeze and stay frozen. The planet would freeze and stay frozen. Not for a season, not for an ice age, forever. There was a time, roughly 700 million years ago, when Earth actually approached this state. Geologists call it snowball Earth, a period when ice sheets may have extended from the poles nearly to the equator. The planet survived. The oceans did not freeze solid from the bottom. And the reason, the only reason, is that ice floated. The insulating layer on top prevented the runaway freeze. If ice had sunk, that mere miss would have been a direct hit, and you and I would not be here having this conversation. And it all comes down to geometry. The angle between the two hydrogen atoms in a water molecule is 104.5 degrees. That specific angle, not 105, not 104, is determined by the quantum mechanical arrangement of oxygen's electron orbitals. It is not a design choice. It is a consequence of how electrons distribute themselves around an oxygen nucleus. And that angle creates the hexagonal lattice that makes ice less dense than liquid water. One angle, one molecule. That is the entire difference between a living planet and a dead one. Think about that. You are roughly 60% water by mass right now. Every cell in your body is filled with this molecule. The blood moving through your veins, the fluid cushioning your brain, the tears in your eyes, water. And the reason any of those cells exist, the reason any biological structure exists on the surface of this planet is because of a bond angle 104.5 degrees. The geometry of a single molecule decided whether Earth would develop a biosphere or remain a graveyard. Let that settle. So the floating ice, that is the first violation, the first rule, water breaks. But the hydrogen bond is not finished, because a liquid ocean on a planet that swings between scorching daylight and freezing darkness is not enough. Life needs more than liquid water. It needs the temperature to stay within a narrow band, narrow enough for proteins to fold, for enzymes to catalyze, for the molecular machinery of biology to operate without being shaken apart by thermal extremes or frozen into immobility. And water does this too through a completely different mechanism. Water absorbs heat like nothing else on Earth. The specific heat capacity of liquid water is 4,186 JWs per kilogram per Kelvin. That is the highest specific heat capacity of any common liquid, and it is not close. Ethanol is about half. Mercury is less than a third. What this number means, in the plainest language, is that water can soak up enormous amounts of thermal energy while barely changing temperature. You can pour heat into water, solar radiation, geothermal energy, waste heat from any process, and the temperature rises slowly, stubbornly, as if the water is resisting, and it is resisting. The hydrogen bonds are absorbing the energy. When heat enters liquid water, the energy goes into stretching, bending, and vibrating the hydrogen bonds, not into accelerating the water molecules. The bonds flex, they absorb, they distribute the energy across the network. You have to overwhelm the entire hydrogen bond scaffold before the molecules move fast enough to significantly raise the temperature. Think about what this means for a planet that is 70% ocean. The oceans act as a planetary thermal buffer, a global shock absorber. During the day, the sun pours radiation onto the surface. The oceans absorb that energy and barely warm. At night, they release it slowly, radiating stored heat into the atmosphere. This is why coastal cities have milder temperatures than inland deserts at the same latitude. This is why San Francisco stays cool in summer, while Sacramento, 80 miles inland, bakes. This is why the tropics do not cook during daylight and freeze after sunset. The ocean is smoothing the temperature curve hour by hour, season by season, millennium by millennium. Here is a way to feel this. Run a bath. The water is warm. Leave it for an hour. Come back, and it is still warm. Now leave a metal pan on the counter after cooking. It cools to room temperature in minutes. Same room, same air, same starting heat. The water holds its warmth because every degree of cooling requires the hydrogen bonds to release energy they absorb. The metal has no such bonds. It gives up its heat freely. That stubbornness you feel in bath water, the way it stays warm far longer than you expect, that is 4,186 JW per kilogram per Kelvin. That is the hydrogen bond holding on. Without water's anomalous specific heat capacity, the daily temperature spring on Earth's surface would be 40 to 60 degrees Celsius. That is what happens on Mars, a planet with no liquid water on its surface. Temperature swings of 200 degrees Celsius between day and night in some regions. No thermal buffer, no mercy. That narrow temperature band that permits liquid water, protein folding, enzyme function, and biochemistry, the band that permits you, exists because hydrogen bonds are exceptionally good at absorbing thermal energy without letting go of neighboring molecules. The thermal stability of this planet is not a geological accident. It is not a lucky distance from the sun. It is a molecular property of one substance. What we are building here is important. The floating ice keeps the oceans liquid. The heat capacity keeps the temperature stable. Each violation stacks on the one before it. Each one is more consequential than the last. Together they create the stage. Liquid water that stays liquid at a temperature that stays livable, on which everything else depends. But the most astonishing thing water does has nothing to do with oceans or climate. It happens in silence, inside the trunk of a tree, in a column of water thinner than a human hair, and it pushes against the limit that not even biology can overcome. Fill a glass to the brim, the very top, then carefully, drop by drop, keep adding water. Watch what happens. The water rises above the rim. It bulges upward, forming a dome held in place by an invisible skin. That skin is surface tension, and water has the highest surface tension of any nonmetallic liquid on Earth, 72.8 millitons per meter at 20 degrees Celsius. Surface tension is what happens when hydrogen bonds at the surface of a liquid have no molecules above them to bond with. They compensate by bonding more tightly to their neighbors at the sides and below. The result is a cohesive film, a net of hydrogen bonds pulling the surface molecules inward and together. In most liquids, this film is barely noticeable. In water, it is strong enough to support the weight of small insects, to hold a dome above a glass, and to do something that looks physically impossible. It can make water flow upward against gravity. This is capillary action. When water meets a narrow tube, a tube narrower than a millimeter, the adhesive attraction between water molecules and the tube wall, combined with the cohesive force of hydrogen bonds between the water molecules themselves, pulls the liquid upward. There is no pump, no pressure pushing from below, just molecular attraction defeating gravity, one bonded molecule pulling the next one up. And this is how every tree on Earth moves water from its roots to its leaves. Now I want you to think about a coast redwood sequoia, several 35 stories, the tallest living organism on this planet. Water must travel from the roots deep underground all the way to the canopy, a vertical journey of over 100 meters through xylem vessels, hollow tubes of dead cell walls thinner than a human hair. There is no pump. Trees do not have hearts. There is no mechanical device anywhere in a tree's trunk pushing water upward. Nothing. Instead, the water is pulled, evaporation at the leaf surface. Transpiration removes water molecules from the top of the column. And because every water molecule in the xylem is hydrogen bonded to the one below it, removing one molecule from the top pulls the next one up, which pulls the next, which pulls the next. An unbroken chain of water molecules bonded end to end, stretching from root to crown. Over 100 meters of continuous liquid, held together by nothing but the cohesive strength of hydrogen bonds between individual water molecules. No engine, no pressure system, no moving parts. Just one molecule bonded to the next for 100 meters, hauled skyward by evaporation and held together by the same electromagnetic interaction that makes ice float and oceans absorb heat. Think about that for a moment. Now here is where it becomes extraordinary. That water column is under tension, not pressure tension. The cohesive strength of the hydrogen bonds is literally holding the chain together while gravity tries to pull it apart. The water in the upper xylem is under negative pressure, a state where the liquid is being stretched, pulled in a direction it does not want to go. As the tree grows taller, the tension increases. The chain pulls tighter. The molecules strain against each other. The hydrogen bonds bear the full weight of a 100-meter column of liquid. In 2004, a team led by George Coe at Northern Arizona University climbed the tallest coast redwoods with pressure chambers and measured the water potential at different heights. What they found confirmed what physics predicted. The leaves at the very top of the tallest trees were operating right at the edge. The water tension in the uppermost was approaching the cavitation threshold, the physical limit beyond which the water column cannot hold. Cavitation is what happens when the negative pressure in the column becomes too extreme. Dissolved gases in the water, trace amounts of nitrogen, oxygen, carbon dioxide, always present in any natural water, nucleate into tiny bubbles under the stretching tension. The bubbles expand. The water column tears apart. An air embolism forms in the xylem vessel, and that transport line dies. This is not a biological limit. The redwood cells could divide further. Its wood is mechanically strong enough to support more height. Its root system can reach deep enough into the soil. The genetics would permit a taller tree, but the physics will not. Coast redwoods at 115 meters are at the theoretical maximum height that the physics of water under tension permits. Coe's team measured it. The numbers are clear. The trees are not merely tall, they are the wall. The hard, absolute, non-biological wall set by the tensile strength of the hydrogen bond in a column of water under gravity. The tallest living thing on Earth. An organism that has been growing for more than 1,000 years, that survived ice ages and wildfires and centuries of Pacific storms, is limited not by its DNA, not by its soil, not by rainfall or sunshine or competition. It is limited by the strength of an electromagnetic interaction between oxygen and hydrogen atoms. A molecular bond draws a line in the sky. And the most ambitious organism on this planet cannot cross it. Let that sink in. Now, there is one more thing water does, and it connects everything. Water's permanent dipole, that 1.85 Dubai charge separation, the same number from the very beginning of this story, is strong enough to rip ionic crystals apart. When you drop a grain of table salt into a glass of water, the partially negative oxygen end of each water molecule orients toward the positively charged sodium ions in the crystal. The partially positive hydrogen ends orient toward the negatively charged chloride ions. The water molecules surround each ion, pulling from every direction, and the ionic bonds holding the crystal together, bonds that are strong enough to keep salt solid at room temperature, strong enough to survive centuries, break. The crystal dissolves, atom by atom, ion by ion. The water disassembles it, not through any chemical reaction, through sheer electromagnetic attraction. The pull of water's dipole is stronger than the ionic bond holding the crystal in shape. Water dissolves more substances than any other common liquid, more than alcohol, more than acetone, more than any acid you are likely to encounter. This is why your blood can simultaneously carry dissolved oxygen, glucose, sodium, potassium, calcium, hormones, waste products, and hundreds of other solutes, all in aqueous solution. This is why the oceans contain measurable traces of every naturally occurring element on the periodic table. This is why the chemistry of life, enzyme catalysis, protein folding, DNA replication, cellular respiration, happens in solution in water, because water's dipole is strong enough to dissolve the molecules that biology requires. The hydrogen bond creates the dipole creates the solvent creates the chemistry creates life. Each link in that chain is the hydrogen bond, expressed in a different way. Remove any link, and the chain does not weaken, it vanishes. You see, this is what makes water not just unusual, but dangerous in the deepest sense of the word. It is not that water has one anomalous property. Many substances have quirks. What makes water extraordinary? What makes it terrifying, if you think about it carefully, is that every single one of these violations is load-bearing. Every one is structural. Remove any single anomaly, and the whole system collapses. If ice did not float, the oceans freeze solid from the bottom up. Life ends. If water did not have anomalous heat capacity, daily temperature swings sterilize the surface. Life ends. If water did not have extreme surface tension and cohesive strength, trees cannot transport water. Terrestrial ecosystems collapse. Life retreats to the ocean, the frozen ocean. If water were not a universal solvent, biochemistry does not happen in solution. Life never begins. Every anomaly traces to the same cause, the hydrogen bond. Every consequence is existential and none of them are redundant. The system requires all of them simultaneously, continuously, on every square meter of the planet's surface for billions of years. Now come back to the beginning. One electromagnetic interaction between oxygen and hydrogen, a dipole of 1.85 dB, a bond angle of 104.5 degrees, the same two numbers from the opening of this story, but now you know what they carry. From that single interaction, ice floats and the oceans remain liquid. The climate stabilizes and the surface stays within the narrow band that permits biochemistry. Water climbs against gravity and forests cover the continents. Molecules dissolve in a solution and chemistry produces life. Remove the hydrogen bond and the universe still works. The laws of physics do not change. Quantum mechanics holds. General relativity holds. Stars still burn. Galaxies still rotate. Nothing in the fundamental machinery of reality is altered in the slightest. Except here, on this one small planet, in this one thin shell of atmosphere and ocean, everything falls apart. Every ocean freezes solid from the bottom up. Every river becomes permanent ice. Every tree is physically impossible. Every cell fails to function. The narrow window of conditions that allows biology, stable temperature, liquid water, solvent chemistry, capillary transport, all of it closes permanently, irreversibly. You exist because of a bond angle, 104.5 degrees between two hydrogen atoms and an oxygen atom. That exact angle, produced by the quantum mechanical configuration of oxygen's electron orbitals, creates the lattice that makes ice float, the dipole that dissolves the chemistry of life, the cohesion that lifts water to the tops of the tallest trees, the heat capacity that keeps this planet habitable. That is the geometry that built the world, and right now you are drinking it.